we're going to try and understand some of the challenges and constraints that we have around how to deploy keyword spotting effectively. We're going to focus on bandwidth, latency, privacy, security, and various kinds of challenges that we have here. I'm not going to go into every single one of those things in extensive depth. Instead, I'm going to try and get you to think about how you should deploy the notion of keyword spotting in a responsible manner. Broadly, I would bring them into performance characteristics like latency and bandwidth from a system standpoint, then from a model standpoint in terms of accuracy and the personalization we expect, and then the safety, security, and privacy standpoint of preserving our data carefully. And then looking at the resource constraints that we have on the microcontroller and how to deploy things effectively. Let's go through each one of these systematically, starting with latency and bandwidth. Latency, the notion here is that we want to be able to provide the results quickly. We want to be able to respond when a user says some sort of keyword. We want to respond very actively. Imagine you say, okay, Google, and you have to wait 3 seconds. Well, do you have any idea how many context switches your brain is doing if you have to wait for 3 seconds? The brain can only focus on things for about 100 milliseconds. So if there's a gap of about 100 to 200 milliseconds, your brain automatically switches off and goes and does other things. So think about that aspect of responsiveness. It's about understanding how we as humans operate in general, and then try to provide the quality of experience from a system standpoint that meets that expectation. And therefore, latency is crucial. When we use a keyword, we want to see some sort of responsiveness. Think, for example, when you have a Hey Siri or Alexa device sitting around. Why do you think they tend to have these kind of lights to communicate that the machine has actually heard you? It's a way for the device to show the human who's interacting with the device that the machine has actually heard them, that it's actually awake and is going to do something now. It gives us a sense of satisfaction to our brain. That's a means to actually mask latency effectively. The fundamental point I'm trying to get across is that latency is extremely crucial because it matters tremendously in deploying keyword spotting applications with this kind of quality of experience. The next one is about bandwidth, right? So here our goal is to minimize the amount of data movement. In any computing system, you've got data and you've got compute. Well, guess which one is the most difficult thing to deal with? It's actually data movement that's really costly. Computing is actually very cheap today. For instance, when you do addition like 1 plus 1, from a pure logical standpoint, it's extremely cheap in terms of energy. But when you have to move data inside the computing processor from point A to point B, that is significantly more expensive, about 1000x more expensive in terms of battery power. So you don't want to send every single word that you say all the way up to the cloud where you have the big computers process the data and then bring it back, because that's going to be very slow and also it's going to consume a lot of energy. So you want to be able to minimize that data movement. The more local you keep the data, the better it is from a battery and lifetime sort of perspective. The next aspect is accuracy. Remember, when you want to enable keyword spotting, you want to wake up the machine. When the machine's got to be continuously listening to us. And it's only got to show the light or some sort of cue that it's actually heard you when it's the right time. Because if you don't want false positives, and neither do you want false negatives. So accuracy is extremely critical. We're going to try and understand what are the fundamental metrics that are used in order to assess keyword spotting. Then there's the aspect of personalization, right? You've got to remember that the machine isn't simply just listening for sounds. It's trying to find interesting patterns in the sounds that happen to resemble a word that might match the keyword. When we do spectrograms, we will understand this much more deeply from a visual standpoint. But in doing that, you will also realize that our sound can sometimes be very similar to some sort of background sound. That sounds crazy, but it's true. So somehow you've got to be able to teach your neural network model to only respond to the user's voice, but also reject any background noise that might seemingly sound like that. So it's got to be very personalized. And you can push this personalization to quite an extreme, specifically if you want the machine to say, like your phone, and you might want to unlock it when it hears you say unlock. Not when my wife say, or my friends or my daughter come by and say unlock. Well, in that particular case, it's got to learn not only the keyword, but it's also got to learn to recognize it's you, in addition to be able to recognizing that it's a keyword. So what's the signature of my voice when I say unlock? You can certainly complement, that perhaps through a camera. So detecting that it's me, has a facial recognition input, and then being able to couple that with the audio signal. But I'm talking about getting a device to respond to you purely based on audio signals, right? So we'll get to do that in code soon. Because your audio signal is data, and we have to move the data, to process it up to the cloud, we have to address security. For instance, if you record the sound and you send it up to the cloud in order to do the keyword spotting, you've got to consider all this data might actually get compromised someday, right? When it's being sent to the cloud. So you want to keep that data secure. The other aspect is privacy. You'll be surprised how little we think about privacy in the real world while we are using all these apps. But when something bad happens to our data, we get very upset about it. It's too late, right? So when data is going up to the cloud, there's a remote chance that the data privacy could be violated. And people can use it in ways you were not expecting. There are several horror stories with smart doorbells, smart home cameras, and smart TVs that violate the user's privacy. So we're going to help you understand what it means to be secure and private about your data and how to do things in a responsible way for keyword spotting. Then, of course, there's the aspect of just overall end-to-end efficiency. Remember that machine learning with TinyML devices are operating on a battery. So we've got to do things with extreme efficiency. And so we have to consume very, very little energy with each of these actions. And the second thing is that memory on TinyML devices is very constrained as well, right? Which means that we have to be extremely good at training our neural network model for keyword spotting to be resource constrained or at least resource aware, so that the network has to be really, really small. And so you'll understand how to do that, how to sort of start with a big bulky network and then how to actually bring it down to fit to down to size. And there are many other considerations that will come up, countless of them, right? But these are the big ones. So hopefully you can recognize why they're actually important. So how do companies actually deal with keyword spotting today, right? It's running on so many devices, because we've got to try and mimic that a little bit over here. And at the same time, I'm going to try and teach you something that's a little different so that you're prepared for what's coming down the road in the future. Today, the fundamental idea is that you open up a box, say, of Google Home device or Alexa device. You've got a microphone that's there that's continuously listening. I'm sorry. Yes, the device is continuously listening, but of course, it's only listening for the keyword. So they say, right? It's not constantly recording the data. It's listening, and that's it. So at some point, what happens is that you might say, Alexa, and at that critical junction, the neural network will pick up those sounds, it will process them. And if the keyword is detected, and if the network is confident enough that it's really a keyword and gives a strong thumbs up, then the remaining part of the data, for instance, when I say, Alexa, dim the lights, Alexa is a keyword part. Dim the lights is a command that is usually offloaded to the cloud, because that requires you to do natural language processing, because to understand what exactly you're saying over there. And that's a very simple example, obviously, but you can actually do even more complex things. For instance, you can say, play my favorite songs. That's a rather complicated process because it needs to maintain a history of what kind of songs you like, and then go pick some songs and then be able to start playing them. And that's a pretty complex process. Now, you might think, for instance, hey, I've got a single device. Sure, I've got this gigantic cloud and that I can run this very large neural network that can do full speech recognition. Well, you're only thinking about your one microphone using a database as a single user, you. But in reality, you've got to remember that there are millions of users out there, billions of Alexa words going out to Amazon on a regular day. And that's a lot of people trying to invoke the thing. Imagine if every single one of these keywords themselves was actually being processed in the cloud, right? Every Alexa as it goes there, not just the rest of the message. That's going to be a huge volume of data going up to the cloud for very simple bits of information. And that would pretty much, I think, melt down the internet. Well, not quite, but you get the concept. There's a lot of unnecessary transactions happening there. Instead, what we really want to be able to do is come up with an architecture that allows us to provide that sort of keyword spotting capability, such as it scales to billions of users. Now, of course, as I've said in part one, we can go out and build these massive data centers, put them right next to resources like waters and wind farms, and that can be cool them down and power them day and night, and build custom processors like the Google TPU that consumes 300 watts of power. And that's not what we want, right? Because we have to scale to billions of users and really bring the whole planet up of these kind of AI capabilities. And this kind of send everything to the cloud is not going to work, because we're going to have a serious energy problem. Why do you think, in fact, Google went ahead to build this custom machine learning processor that consumes so much data? It's specifically because you need to be able to run this extremely efficiently. So yes, they ended up building a custom processor, but if they did not do this, they would be using so much more power just using regular CPUs and GPUs per processor in order to be able to handle OK Google, for instance. And what are we trying to get to, right? We're trying to get to something that would run on the order of milliwatts or microwatts with extreme efficiency, which is mind-blowing. I know, and it's really complicated, right? So we have to somehow figure out how to be able to run the keyword spotting sort of task on this tiny ML device. So keyword spotting allows us to wake the machine up and then provide some complex backend services, rather than having every keyword actually going all the way up to the network. So it's a very powerful system level optimization. And this is one of the reasons why keyword spotting has become ubiquitous on so many devices. And of course, as I said earlier in the previous video, you can do much more than keyword spotting. You can actually expand and do keyword spotting with a limited vocabulary set. You could potentially do dim the lights also on the microcontroller. That's an extension of a very specific, more than just one word to wake up the machine. And that's doable, and we'll get there, and I'll show you how we can do that too. So what I'm trying to get across to you is that these constraints and these challenges that we have spoken of, you really need to understand the full end-to-end picture and why keyword spotting has become so important. There are, of course, latency, bandwidth, security, privacy, personalization, accuracy, memory constraints, battery constraints, right? All of these aspects which we just discussed. You need to think about, building this model, as an end-to-end and then scaling this model up, right? So you need to be aware of the full end-to-end picture on how this particular ML application is deployed in the bigger context, right? For billions of users. And hopefully you get a little sampling of that. We will soon start going into the machine learning pipeline that's involved in building the application. And we will be building some of these with these constraints and challenges in mind. So I'll see you in that lesson.